I'm introducing a new topic in physics, which is the electromagnetic induction. Under its introduction, we are going to look at the phenomenon of electromagnetic induction, which can be demonstrated by an experiment. To do this experiment, we need a wooden cylinder and an insulated copper wire. So the first thing is that wind an insulated copper wire on a wooden cylinder so as to form a coil in the solenoid. Then connect the two ends of the coil to a galvanometer and place a magnet close to it. When the magnet is stationary, the galvanometer is 0. This shows that provided that the magnet is not in motion, no EMF is induced. The point of the galvanometer deflects towards the right when the north pole of the magnet is moved towards the solenoid. This implies that EMF is induced only when the magnet is in motion. And when there is no motion of the magnet, the galvanometer shows a 0 reading, which implies no current flows in the solenoid. Considering the fourth case, that is, when the magnet is moved away, current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the other side, which is the left. For the fifth case, that is when the magnet is moved away with greater velocity, meaning if we try to move the magnet in and out of the solenoid at a greater velocity, the deflection is much. And similarly, when the polarity of the magnet is reversed and the magnet is brought closer to the solenoid, the current flows in an opposite direction and the galvanometer accordingly tends towards the left, as illustrated. Now, in line with Faraday, he observed that current flows in the coil only when there is a relative motion between the coil and the magnet. Thus, no current or electromotive force is induced when the magnet is stationary. The direction of deflection in the galvanometer is reversed if the direction of motion is reversed. This is demonstrated. Away from that, let us consider the factors leading to increased current in the coil. The first one is by using a strong magnet. The second one is by increasing the velocity at which the magnet moves in and out of the solenoid. And the third one is by increasing the area or the number of turns of the coil. In addition to this, taking you backwards, that is to case 1, when the magnet is stationary. According to Michael Faraday, there is no relative motion between the magnet and the coil, and the magnetic flux within the coil remains constant, so the galvanometer shows no deflection. I think this is clear, as we can see the illustration there. But when the magnet is moved towards the coil or vice versa, the magnetic flux changes and an EMF is induced in the coil. If the circuit is complete, the EMF causes current to flow through it. This is self-explanatory, as we can see the arrows showing the flow of electric current. Now this table simply shows the summary of the position of the magnet and the deflection of the galvanometer, which in itself demonstrates that when the magnet is at rest, no deflection is observed, meaning no current induced. For Faraday's law of induction, we can say that whenever there is a change in the magnetic flux linked with a coil, EMF is induced. Under this law, factors affecting the magnitude of the EMF includes change in magnetic flux and also time in which the flux changes. The direction of the induced EMF depends on whether there is an increase or decrease in the magnetic flux. On this one, we are simply looking at how close the magnetic field lines are. John A. Fleming gave two rules to determine the direction of motion or the direction of induced current, and these were called or are referred to as one, the Fleming's left-hand rule, and the second one is called the Fleming's right-hand rule. Now, the left-hand Fleming's rule is used on electric motors, while the right one is used on generators. For the Fleming's right-hand rule, the thumb represents the direction of the magnetic field. The thumb represents the direction of conductor, or the direction in which the conductor is moving. Then the forefinger represents the direction of the magnetic field lines, and while the middle finger represents the direction of the current which has been induced or produced. Hence, this Fleming's right-hand rule can be used to predict the direction of induced current. To understand this better, we have another law which is referred to as Lenz's law. Now, this Lenz's law is based on the direction of current as induced by the presence of magnetic field lines. Lenz's law is in line with Newton's third law of motion, which states that to every action there is always an equal and opposite reaction. It also obeys the law of conservation of energy, which states that energy can never be created or destroyed. Faraday's law of induction is based on Lenz's law, or rather, Lenz's law depends on Faraday's law of induction. And this Lenz's law states that when an EMF is induced or generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produces it. In a nutshell, whenever there is change in the magnetic flux, linked with a coil. An EMF is induced. With this, we call it a